Welcome. We're going to do a quick review of what we covered for Chapter 2 for atoms, molecules, and ions in class on Wednesday. We're going to think about how we can design and implement methods of gathering information and data to answer a question. A doctor orders that a patient receive 1.5 times 10 to the negative third mole of sodium chloride. The only solution available contains 1 gram per 100 milliliters of solution. A mole of sodium chloride is equivalent to 58.5 grams of sodium chloride. How much of this solution should be given to the patient? So this is again making sense of dimensional analysis or unit conversion. And so we're going to take the information that we're given, which is the moles or the amount of sodium chloride that we have, and then we're going to use this conversion factor, which is 1 mole of NaCl is equivalent to 58.5 grams of NaCl. That allows us to cancel the unit of moles. Now we have grams. And in order to be able to convert from grams to liters, we're going to need to use a density equivalent. And that's really what's given here, this 1 gram per 100 milliliters of solution. So 1 gram of NaCl is equivalent to 100 milliliters of solution. So my grams then can cancel. And what I'm left with is milliliters, which is the unit for volume. So I'm going to multiply across the top. I'm going to divide by what's on the bottom. That's going to give me 8.775 milliliters. But it's really important that I think about my significant digits here. And so in this case, my significant figures or my significant digits, folks use those words interchangeably, is 2. So I want to make sure that I have 2 sig figs or 2 significant digits for my final answer, which is 8.8 milliliters. Thinking about norms so that we create a space where we can all learn. We want it to be safe. We want everyone to feel comfortable. This is really important. That means that questions are always welcome. So if you have a question and you're worried about whether or not you can ask, you should always ask, because the brilliant scientists that I know are ones who ask questions. So by asking questions, you are being a scientist. Being able to know that you can rely on others. So we're going to build this practice of collaboration, and that will take time for you to become familiar and comfortable with people that you're working next to or with or beside, but we're going to build that. And then this idea of iteration. I want you to take risks. And the only way that most folks feel comfortable taking a risk is if they know that they can try again. So that's really important. We're going to practice that. I shared about our scientist spotlight. So in this case, Crystal Tsozi. So she's Navajo. She's a geneticist and a bioethicist. She's actually the co-principal investigator for preeclampsia, which is a condition in pregnant women that involves blood pressure. And she's studying this in the Turtle Mountain Band of the Chippewa. She also is looking at policies for data privacy, biobanking, and building research space. So she has her master's degree, but she's pursuing a PhD. And so she's a really great example of a scientist who is working to make sense of both the science and to create policy that is informed by the science. So I think she's a really great example of a scientist to spotlight. We're going to take a look at learning outcomes. So we're going to be able to distinguish between empirical and molecular formulas. We're also going to be able to distinguish between ionic and covalent bonds. We're going to distinguish between ionic, molecular, and acidic compounds. And then we're going to be able to recognize diatomic elements and polyatomic elements such as P4 and S8. And then we are going to start, but probably won't finish, naming molecules, ionic compounds, and acids. And we're going to start to work on correctly writing formulas for ionic compounds, molecules, and acids, but we'll pick this up on Monday. So in your notes, I asked you to create a model for an atom. In this case, we had the actual size of the atom, and then we had our model size. So while the actual size is 10 to the negative 15th meters, our model size is going to be centimeters. And so an equivalent model would be an apple. So in this case, we're saying our proton would be an apple, and then you did some brainstorming together, and you came up with, say, for example, that a neutron could be an orange, that an electron could be a speck of sand, which means that our atom would be 6.2 miles. So it's really important and valuable for us as scientists to think about the benefits and the limitations of this model. So the benefits are that it's something that we can see, at least apples and oranges in our nucleus. But I wonder if you were standing and trying to glimpse a speck of sand from 6.2 miles away, could you see it? So even our model that is making the atom more visual for us still has some challenges or limitations. And that's something that we're always going to be thinking about as we approach models. Another example of the way that we can make sense of new information is by using the chemist triangle, and in this case, our symbolic representation. So different types of chemical formulas can convey different types of information. For example, an empirical formula conveys the relative number of atoms of each element in a compound. This is the lowest overall ratio. We often see this for ionic compounds. And this is when we do elemental analysis, where essentially we consume or burn a molecule to find out what it's made of. These are the results typically reported in terms of the empirical formula. And then the molecular formula is the actual number of atoms of each element in a molecule. And finally, the structural formula are the actual atoms and some of their connectivity. So as we think about today, we're going to do some science practices associated with the information that we're learning. We're going to ask questions and define problems. We're going to analyze and interpret data. And then we're going to think about constructing explanations and designing solutions. What's really interesting and important about these is that eventually that's going to allow us to engage in argument from evidence. So here's an example of a science practice, asking questions and defining problems. Can you identify the type of chemical formula? So hopefully you were able to see that these are structural formulas and that these molecules, right, have a different arrangement of atoms. Hopefully you were also able to see that although they have a different arrangement of atoms, they have the exact same molecular formula. Here we asked you to identify the type of chemical formula, and hopefully you noticed that this is an empirical formula because it's the simplest overall ratio, whereas this is the molecular formula that could be simplified by dividing each of these numbers by 2. When we thought about analyzing and interpreting data, the example that we used from class was taking a look at our periodic table. It's really important that you're able to recognize the difference between a period, which is the row, and the group, which is the column. We're going to use that information as we study main group elements like the metals. These are the first 2 groups, as well as the nonmetals. We're going to also take a look at some of the transition elements. And while we probably will do some work with intertransition metals, they're probably outside of the scope of this course other than understanding where they fit in the periodic table. So I want you to be able to calculate the molar mass of a diatomic molecule. So I don't care which one of these you pick. I want you to be able to use your periodic table to come up with a molar mass for, say, for example, oxygen. So you're going to choose one diatomic molecule and you're going to calculate its molecular weight or its molar mass. These 2 words are interchangeable. You'll see folks use them fairly frequently. I want you to calculate the mass of 1 mole of the molecule you chose. That's really what that means. So for example, if you were to do hydrogen, you would add, right, 1.008, which is the mass of 1 hydrogen, the mass of another hydrogen, and that would give you 2.016 grams per mole of H2. I noticed, and actually Arlene was gracious enough to point this out, that sometimes this B, all by itself, could be confusing. So please don't confuse this with boron. This B actually represents bromine. So if you need to, make it a blue B and a blue R. That way you can keep it straight. We also talked about arguing from evidence. And so in order to do this, we're going to use a structure. The structure that we're using is something called claim evidence reasoning. So what is a claim? A claim is a statement that answers a question based on your observations. You want to make sure that your claim answers the question, is direct and to the point, and then that it uses key terms, ideas, and information from the question. So what about evidence? What is evidence? Evidence is scientific data collected through observations and measurements. You want to make sure that your evidence includes data and observations from measurements, and that it identifies patterns in the data. And then reasoning. So what is reasoning? Reasoning is your evidence of why the evidence supports your claim. So we want to make sure that your reasoning cites scientific reasons for each piece of evidence that supports your claim, and that it demonstrates an accurate understanding of those scientific principles. So we're going to do a practice. We're going to argue from evidence, and we're going to say, what type of bond does hydrogen form? Is it ionic? Is it covalent? Or is it both? And we're going to use this image or this model to make sense of that. So our claim is that hydrogen participates in both ionic and covalent bonding. Our evidence is that when hydrogen is bonded to the nitrogen, it shares its electrons. When hydrogen transfers an electron to chlorine, it forms an ion. Our reasoning is that when electrons are shared, this is a covalent bond. When electrons are transferred, these are ionic bonds. We'll have the opportunity to practice making claim evidence reasoning statements, but it's really important that you think about the structure of arguing from evidence as a tool. It's going to be one of the best assets that you have in your toolbox when it comes to studying science at any level. That's in your Chem 110 class, that's when you take upper division electives, that's when you go on to graduate school, and it's even when you win a Nobel Prize. Scientists argue from evidence. That's how we think. That's how we make sense and communicate the information that is important regarding any topic. Okay, a reminder about science student success. This is S cubed. Again, we're going to meet from 11:30 to noon on Mondays and Wednesdays to solve problems. All are welcome. And then the Chem 110 discussions are Thursday in the library at 11:28. If you have not attended discussion, you want to make sure to do so. And then we talked about this during the last 5 minutes of class. I want you to practice this week, because this is going to be graded next week. It's going to be an assignment you're going to complete in class. And then last but not least, you want to make sure that you are, I got to change this. This is for next week. So by Sunday, and this is going to be February 2nd. I can't believe it's already February. You want to make sure that you're reading chapter 3 in Alex, because we're going to have our week 3 lecture 1 reading quiz that's going to happen in class on Monday. And then we'll have new material that we're going to take a quiz on Wednesday in class. All right, thanks so much. Hope you have a great day. I appreciate your hard work, focus, and attention to detail.